Hi friends, welcome to my channel Interesting Engineering. Today let's discuss about Wheatstone bridge method. So this is a bridge method used to measure the value of resistance, the medium resistance values accurately over the range of 5 ohms to 1 mega ohms. So the medium resistance in the extreme lower end and in the extreme higher end of the medium resistance, this bridge will be showing some inaccurate results. So what may be the reason behind the inaccuracy and how to eliminate such errors, that we shall see in this video. So this bridge is used in finding resistance of motor windings, relay coils, transformer windings. So this is a bridge circuit used to measure medium resistance value. It operates on the principle of null balance. Null balance is nothing but the galvanometer, the detector used in this bridge circuit, shows null deflection under balanced condition. So that's the concept used here. And regarding its construction, it consists of 4 ratio arms, where 2 ratio arms consists of a fixed resistors. It's a non-inductive resistance, and one arm of the bridge circuit consists of unknown resistor whose value is to be found out, and in the other arm of the 4 arms of the bridge circuit, we have a variable standard resistor which is being adjusted to find the resistance of this unknown resistance. And this entire bridge arrangement is connected with a voltage source, and to determine the resistance value, we make use of a detector. Here we make use of a galvanometer. So this galvanometer acts as the detector, and the balance condition is achieved under zero deflection of this galvanometer. So this is the construction feature of this Wheatstone bridge circuit. And here when we connect the voltage source with this bridge arrangement, there flows current through the bridge circuit. So initially when voltage E is applied to this Wheatstone bridge circuit, the current I1 flows through the ratio arm P, and this current enters into the galvanometer, branches out into this galvanometer as well as to this branch, Q branch, and in the ratio arm, in the variable resistance arm, there flows current I2 that to enter into this galvanometer branch as well as to the standard resistance branch. So due to the presence of voltage source here, there flows current through each arm of the galvanometer, each arm of the Wheatstone bridge. So under balanced condition, the potential drop across the points PAB will be equal to PAD. So the bridge is brought to a balanced condition by making the potential across the points PAB made equal to the potential across PAD. So at that condition, the current through the ratio arm I1 will be equal to I3, and similarly I2 is equal to I4. These two conditions are achieved for a bridge balance condition. So under bridge balance condition, the potential drops are equal as well as the current through two ratio arms I1 and I3 will be equal, and I2 will be equal to I4. So these conditions are maintained under balanced condition. So under balanced condition, since the potential drop across these 2 points are equal, since the potential drop between these 2 points are equal, there flows no current through the galvanometer. So at that case, the galvanometer current will be 0, that is Ig equal to 0. So it acts as an open circuit. So at that time, the standard resistor is adjusted in such a way that there flows no current through the galvanometer. So the value of this adjustable resistor represents the value of unknown resistance. So let's derive the equation equation for unknown resistance now. So here potential across AB is equal to potential across AD, I said. So what will be potential drop? So potential drop is nothing but potential drop across these 2 points PAB, that we can represent as potential equal to current into that particular resistance. So we can write it as I1 into P. So the potential drop across the point AB will be the current through the resistor into the value of resistance. So I have written it as I1 into P. And PAD, what is PAD? The potential drop across these 2 points. PAD is the potential drop across these 2 points, and it can be represented as I2 into R. So I am writing it as I1P equal to I2 into R. Similarly, the potential drop across PBC will be equal to potential drop across PCD. So what is potential drop across BC? It is nothing but I3 into Q. So this is, let me consider it as equation number 1. Then comes equation number 2, which is nothing but I3 into Q is equal to I4 into S. This is equation number 2. So as I said earlier, I1 is equal to I3 and I2 equal to I4. So I am replacing I3 and I4 by I1 and I2. So we can write it as I1 into Q is equal to I2 into S. Then let me represent it as equation number 3. Now I am going to find the ratio of equation 1 to equation 3. So equation 1 divided by equation 3, we can write it as I1P divided by I1Q is equal to I2R divided by I2 into S. So since I1 is there at both the numerator and denominator, I am cancelling it out, and I2 cancels out. So the remaining term will be P by Q is equal to R by S. So we need the value of unknown resistance R. So I am multiplying it here. So R will be equal to P by Q into S. So this is the equation for unknown resistance. R is equal to the value of known resistances P by Q into standard resistance S. So when we check in this resistance equation, it is independent of voltage source. So in this bridge circuit, the unknown resistance R is independent of the voltage source used. So we can make use of any sort of voltage source here. So this resistance R, unknown resistance R, is, can be calculated by P by Q into S. So this is our resistance equation. So in this equation, we need to find out the value of P, Q and S by means of which we can able to calculate the value of unknown resistance R. So this is the general equation for a Wheatstone bridge circuit. But even in this case, in this bridge circuit also, we have certain sort of limitations, such as in each resistors there occurs leads connected to it, and also there occurs contacts over here, which may cause error in our measurement. Due to the presence of leads and contacts in the resistances, there occurs errors. And also due to the passage of current through these resistors, the current through these resistors will be very less, due to which the galvanometer cannot be able to sense those values, current values, due to which there may occur certain error in this bridge circuit. So these two are the major drawback of this Wheatstone bridge circuit. One is the lead resistance and the contact resistance, and the other one is the current through the galvanometer. If it is less, it can't able to detect. So that too causes error in this Wheatstone bridge circuit. So those things we can eliminate by making use of certain modifications in this bridge circuit that we shall see it in our next topic. So what may be the sources of error in this Wheatstone bridge? It is nothing but the limiting error of resistor. Since we make use of 4 resistors in this bridge measurement, each resistor will be having some sort of limiting value that too affects our measurement. The second one is the insufficient sensitivity of detector. So as I said earlier, the galvanometer will not be able to detect a little amount of current, so it may not show any sort of deflection. That too causes error in our measurement. Then change in resistance due to heating effect. So since we make use of a resistor here, when we increase the current value through these resistors, there occurs heating problem of these resistors that too cause certain error in our measurement. And the resistance of leads and contacts. So the leads and contacts are present in this bridge arrangement, that too adds up in our measurement. So due to which also there occurs error in our measurement under lower end of medium resistance values, as well as a higher end of our medium resistance values. That's the major drawback in our Wheatstone bridge circuit. And also there occurs thermal EMF problems. So these thermal EMF, that is due to the presence of heating effect of resistors, that causes some sort of variations in our measurement. So these are all some of the problems that could be present in a Wheatstone bridge circuit. But rather than that, the Wheatstone bridge circuit is most accurate measurement technique used for measuring medium resistance values. So this is our derivation part. So in our derivation part, we made the bridge balance condition. So under bridge balance condition, we have certain potential equal potentials, by means of which we have derived the equation for unknown resistance. So this is about our Wheatstone bridge method. So in our next video, let's discuss about Kelvin double bridge method. So for more videos, keep watching. Please subscribe and share. Thanks for watching.